So the next speaker is Romain Dubessy. So Romain is professor at Sorbonne Paris Nord University. He is an expert in superfluid dynamics in low dimensions, and currently he investigates the physics of fast rotating atomic gases trapped in a curved surface. So please, Romain, you can start.
Okay. Okay, thanks, Luigi, for the introduction, and thanks for organizing this wonderful conference. So the talk I will present today is not strictly speaking in the context of atomtronics, but it will be an experimental talk, and I will show what recent results we obtained in the BEC group at Villetaneuse, so it's University Sorbonne Paris Nord, about trapping atoms on a curved surface and setting them in motion onto this surface. And we already heard last week from the talk from Wolf von Klitzing, sorry, about this adiabatic potential. So here I will use mainly magnetic fields to trap the atoms and manipulate their motion. And the idea is that we get for free confinement to a surface by using the combination of magnetic field and radio frequency fields. And the idea is that we will select one isomagnetic surface through a resonance condition, and I will show it in more details in the next few slides. So basically what you get with this kind of techniques is a strong confinement to the surface and very smooth surface potentials, as we heard previously. So before going into the technical details, I will want just to give you a little introduction to the experimental setup we are using in Villetaneuse. So we trap rubidium atoms and we make a Bose-Einstein condensate. Starting from a two-dimensional mode, we load a three-dimensional mode, so it's fairly standard setup. And then we load the atoms onto a purely magnetic trap that is made of two large coils in anti-Helmholtz configuration that produce a quadrupolar field. And these coils, it's the big blue disc here, are mounted onto a translation stage, and we move the atoms by about 30 centimeters to our science cell. So the science cell is a tiny glass cell that you can see here among all the coils where the green light is shining. And we do so to get the atom away from the mode where the pressure is fairly high and to get a long lifetime in our trap in this science cell. Then we transfer into a much smaller quadrupole trap with small coils that enable us to produce higher gradients. And in this quadrupolar trap, we achieve Bose-Einstein condensation. So for technical reasons, we have to use a green light in the beginning of the experiment. That is to plug the hole of the quadrupole trap and avoid Majorana losses. But apart from this step, we will use purely magnetic trapping. In the following slides, I will show you some pictures of the atomic density, and we record such densities along two axes, either the horizontal imaging axis, and in that case, we take what we call time-of-flight pictures. So it means we release the trap, let the atom expand, and record a density profile after free expansion. And this density profile is reflects the momentum distribution of the gas. Whereas when we do vertical imaging, we can do either in situ imaging to look at the atoms inside the trap, or after a time of flight to see the in-plane momentum distribution. So going back to the bubble state, so the surface, we achieve this trapping by using a magnetic field. The important point here is that it's an inhomogeneous magnetic field, such that if we follow the spin state of our rubidium atom, so it's in its ground state, it's spin 1 atom, we have 3 energy levels that are whose energy depend on position with respect to the center of the trap in this way. So we have one atomic level that is trapped, the other doesn't feel the magnetic field, and the last one is anti-trapped. And the one we are interested in is the m equal +1, but it's trapped at the minimum of the magnetic field, the norm of the magnetic field. And what we now do is to shine radiofrequency photons onto this system, and these radiofrequency photons will select a particular energy scale, magnetic energy scale, and induce a resonance between the spin state. And if you go to the dress state basis, meaning you remove one the energy of one photon from the upper state, you add the energy of one photon to the lower state, you realize that all these states are almost degenerate, and there are some level crossing. And what we know from quantum mechanics is that when there is a coupling between these spin states, then we won't get just a trivial level crossing, but in most cases, an avoided crossing. And this avoided crossing provides us with a trapping mechanism that is directly linked to the initial selection of the isomagnetic surface by the photon field. So what is nice is that you can work out things almost always analytically and write the resulting potential within some rotating wave approximation assumption in a very simple way. It depends only on 2 quantities: the local detuning of the photon energy with respect to the bare magnetic state and the local coupling between the spin state. And both those quantities depend on the position in the trap. And if the atoms want to minimize their energy, they choose to cancel the detuning term, and they are left with their magnetic coupling energy. And this allows us to create this surface trap. Furthermore, we can even control better the system by adding additional radiofrequency fields. So for example, we use extra fields at a different frequency omega prime to induce now spin transition between the dressed states in order to, for example, in this case, truncate the potential at a given energy. And this gives us a control over the sample temperature. Okay, so now if I show you a picture of the full surface, if you look at the cut through the trap, you get the iso potentials and you get the resonance surface you can guess here. And because we are on Earth, there is gravity coming into play, and gravity acts on the atoms by pulling them to the bottom of the surface. So in this trap, if we do nothing special, the atoms are gathered at the bottom of the surface, and we are left with a trap that is very well described by a highly anisotropic harmonic trap with vertical confinement of the order of 1 kilohertz and in plane on the bubble confinement that is just given by a pendulum frequency due to the combination of gravity and the constraint that the atom move on this surface. And what is nice is that we are left with some degrees of freedom. So we can choose the radiofrequency polarization, or we can choose the radiofrequency frequency, omega itself. And this will enable us to tune this bubble. So for example, we can realize rotationally invariant trap with circularly polarized for a particular choice of circular polarization of the RF field, or we can induce anisotropy with linear horizontal polarization. And we can change the bubble radius quite easily by changing the photon frequency. And we have shown that this kind of trap was ideally suited to study two-dimensional trapped gas dynamics. So in the next 20 minutes, I would like to talk about two recent results we obtained with this trap. So the first one is the study of fast rotation in such a system. And the second one is to explore a gravity compensation mechanism to try to fill the whole bubble. So first, fast rotation in a bubble trap, and this work was published last year in Paris. So what's interesting about rotation with Bose-Einstein condensate is that it is well known that they admit rotation by nucleating vortices, and we can, in the experiment, see the vortices by letting the gas expand and taking a time-of-flight picture from the top view and seeing all these points where the density vanish inside our gas. Now I would like to show you that we will be able to explore a peculiar rotation regime where the vorticity somehow gather in a central hole and form what we call a dynamical ring, that is a ring shape stabilized by the rotation. So to motivate further the idea of studying rotations, one can think of one of the original motivation for this kind of studies was to take advantage of the analogy between the ideal two-dimensional trapped rotating atomic gas and the two-dimensional electron gas in the presence of a uniform magnetic field. If you write this Hamiltonian, you can apply it to both systems just by making some translation between rotation and magnetic fields. And what is particularly interesting in this setup is that if you rotate fast, and fast means that you rotate close to the trap frequency, the level structure of the harmonic oscillator change, and you are left with a Landau level structure with a highly degenerate ground state that that will result in some very interesting many-body correlated state. So this was a long time ago the motivation to make such studies, and now with the experience we know that a more promising approach that recently gave very beautiful results is to use artificial rotation with gauge fields in synthetic dimensions. And I think in the group of Jean Dalibard, there are very beautiful recent experiments about that. So in this talk, I will show to you what we can do in the bubble trap when we try to rotate fast. So first, how do we rotate? We induce anisotropy in the trap. So we change the dressing polarization that is produced by these two square dressing antennas. And we make it such a way that the trap is now slightly anisotropic, and we can choose the angle at which the anisotropy takes place, and we can make this angle rotate with time in a very controlled way. And this particular shape induces a coupling to a quadrupolar mode of the BEC. And we know that for our system, we will have a resonant coupling at about 24 Hertz of rotation that will that should enable us to nucleate vortices. So when we do the experiment, we indeed see that we create a vortex lattice when we rotate at this frequency, and we can try to rotate faster. We see that we increase the number of vortices, and then things get a little bit more complicated as we see that the system expands. There are more and more vortices, but it is difficult to see the individual vortices, and we have possible effect of temperatures or phase fluctuations that explain this vortex that is melting. So this kind of experiment is not new at all, because almost 20 years ago in the group of Jean Dalibard or Eric Cornell, the same kind of experiments already demonstrated these effects. The only difference here is that here we start from a two-dimensional gas, and here the experiment was done in a three-dimensional regime. So what can we do? What is the new physics that we can achieve here? First, can we reach higher rotations? And the main problem in these experiments is that the centrifugal force, as we rotate faster and faster, will compete with the harmonic trapping. And this can be mitigated if you add extra terms to your potential. So for example, in the rotating frame, the two-dimensional harmonic oscillator potential will read like this. And when the rotation frequency is equal to the trap frequency, you cancel this harmonic trapping term, and you lose the atom, basically, because there is no trap anymore. One idea that was explored in the group of Jean Dalibard is to add higher order potential terms in the potential. So for example, quartic terms that help to stabilize the system at large rotations. And in fact, if you go faster than the trap frequency, you will get this kind of Mexican hat potential. And in fact, our trap, the bubble trap, has all these higher order terms because the atoms cannot go far away from the center. They are constrained to move onto the surface. And these kind of harmonic with quartic potentials are also interesting because now if you study what is the ground state as a function of the rotation, you find that starting from a regular vortex lattice, as the rotation increases, some vertices will merge in the center and a hole will start to appear, eventually leading to what is called the giant vortex state, when all the vortices have entered this central hole. So what happens in our experiment? In our experiment, if we rotate fast enough and we let the system evolve and thermalize, we observe that after some time, so these are quite long time scales for atom physics BEC experiments, so it's a thermalization process, we observe that at the center, so in situ inside the trap, there is a hole that appears in the density distribution. And if we lower our RF knife, meaning we lower the temperature in the system, so we perform forced evaporation, we see that the hole increase in size, and that therefore the rotation is faster, gets faster. And this acceleration of rotation, we explain it by a selective radio frequency evaporation, because atoms are removed selectively near the center of the trap. And this gives access to a new regime where the atoms form a stable ring. So this we call a dynamical ring. We are not in the giant vortex state yet, but we can see that we recover a very smooth profile with absolutely no density near the center, and that what we measure match quite well the expected Thomas Fermi distribution in a rotating frame, and is quite far from, for example, a gas at the critical temperature. So you can say, okay, this is just another ring. We have seen many rings produced by different technique in the past week. What is so special about this ring? What is special is that it's rotating very fast. If we perform a time of flight expansion on this system, we see that the expansion is almost purely ballistic, and the size of the system grows with time of flight, as what you expect for a ballistic expansion. And if you fit this growth, you find that the rotation frequency corresponds to a linear velocity along the circle of the order of 7 millimeters per second. And if you compare this quantity to the speed of sound that you can infer from the peak density in the cloud, you get something that is almost 18 times the speed of sound. So we get a BEC, a superfluid that is flowing at Mach 18 with respect to this own speed of sound. And we heard already something about this kind of hypersonic motion in atomic waveguide last week in the talk by Wolf von Klitzing. So here, I would just like to show to you why I say it's a degenerate gas, because we have probed, in some sense, the coherence of this system by performing a quadruple mode spectroscopy. So quadruple mode spectroscopy means that we apply a small deformation to the trap and we rotate at some excitation frequency, and we see how the system reacts, and we get a resonance. And the position of this resonance depends on the rotation of the system itself. And what is surprising to us is that when we cross the rotation frequency where the hole forms, we see that this quadruple mode goes from the counter-rotating side to the co-rotating side with the flow. And this is not something that you can explain by, for example, sum rule calculations that are usually used to compute these spectra in these Bogoliubov spectra in atomic cases. So this is something yet to be understood. So now I would like to move to the last part of this talk, and I would like to talk about dimensional reduction in the bubble, or how can we try to fight gravity and let the atoms fill the whole bubble. So the motivation for this experiment is to realize that if we were able to have a system filled, a bubble surface filled with atoms, it would be a very interesting system to study rotation, because it would be very different from a plane, for example. Because in this system, in this closed surface, when you have one vortex line, this vortex has to cross the full system and go from one side to another, and therefore create two vortices. So vortices will come by pairs.
Romain, you have 8 minutes.
Okay, fine. Thank you. And this has recently drawn a lot of interest with quite a few recent theoretical works to address the physics of superfluid and BEC on such a geometry. And these works were motivated by the fact that since a year or so, there is a BEC machine on true microgravity environment about the International Space Station. And among all the proposed experiments, there is one experiment that has to do with a shell-shaped BEC that will be produced using the near field magnetic field of an atom chip. So it's a different geometry, and RF antenna to dress this field and realize a kind of bubble trap. And here, what is expected is that without gravity, the atoms should fill the whole surface of this dressed bubble trap. Our question is, can't we look for this physics on Earth? So can we make use of the full bubble surface that we have already in our lab? And if you remember my little introduction to these traps, if the atoms are localized at the resonant condition on the shell, the detuning is 0, and then the potential is simply the coupling energy plus so the total potential is the magnetic coupling energy plus the the gravitational energy. And the idea would be to fight against this force that pulls the atoms towards the bottom of the trap. And it turns out that if we choose a circularly polarized RF field, and if we assume that the atoms follow on the surface of the bubble, then this magnetic field coupling is written like this and is exactly opposite to the gravity with a kind of anti-gravity effect. And if we tune the parameter to choose that both terms linear in Z balance, then we can get to a situation where the isopotential of the trap really fill the whole surface. So this is what we try to do in the experiment. And so let's look at the results. This picture shows the in situ atomic distribution in the trap. This is from the top view. These are actual pictures. This is the result of a Gross-Pitevsky simulation for the same parameters. And this is for increasing gradients. So we will tune the gradient of the quadrupole trap. So when we increase the gradient, we see that the atoms start to fill the whole available space and seems to go up to the circle here that is the limit of the equator of the bubble. And then when we increase further the gradient, we find that instead of filling the whole bubble, the atoms start to form a ring and stabilize in a ring geometry again. And this is confirmed by the simulations that says that the atoms localize at some given heights on the bubble. So why is that? What did we miss in the previous explanation? What we missed is the fact that the transverse trapping frequency is not constant. So this is a kind of subtle effect that we didn't thought in the beginning, is that when you assume that the system will be two-dimensional, you still have to take into account the 0 point energy of the transverse confinement, because it's not homogeneous on the whole surface. And you can see it in the difference between the isopotential here and there that are more spaced here and closer near to the top. So in fact, our total potential on the surface reads like this, is corrected by this term. And this term, it turns out that it's minimal close to the equator, and it diverges at the North Pole. So it repels the atoms from the top of the bubble. So the atoms could never go up to this point and will stop at some finite position. In the end, we made a long study to understand this effect and the different effects. So we found that there are two effects competing. So the first one is this transverse energy coming into play that modifies the potential. So this is the term that makes the energy increase a lot for angles close to the top of the sphere. And we have also new effects that we usually don't take into account into our magnetic potentials, is the fact that as the atoms climb the bubble, they see different effective polarization of the radio frequency field. And precisely, there is now a sigma minus term. So even if at the bottom the polarization is perfectly circular, on the side of the bubble, there is no sigma minus term that induces a light shift in the detuning. And there is also a parallel component pi that amounts to a reduction of the Rabi coupling. And with all this, we get...
Yeah, I have 3 minutes.
Yes, I come to my conclusion. And with all this, we get a good match between this model that allows to compute this kind of profiles with the full numerics. And we can predict now the position of this annulus and its width quite easily. And so I would like to just to mention that this system results in an annular gas that is only stabilized by the dimensional reduction. So it's truly the third dimension that makes these atoms take this ring shape. So now I would like to summarize and conclude. So I have shown to you experiment about fast rotations on a shell. And we have seen vortex lattices that we have a possible lattice melting mechanism when the rotation is too fast. But if we let the system thermalize, and thanks to selective spin-up evaporation, we can observe long-lived dynamical ring flowing at Mach 18 for tenths of seconds. And now what we want to do with this setup is investigate the decay mechanism. So look at what will happen if we add an obstacle on the path of the atomic flow. And in the second set of experiments, I explained a novel gravity compensation mechanism for this quadruple dress trap. And I have shown that it enables to explore a large fraction of the bubble surface, but at the cost of forming annular shape at some point, induced by the, and this localization is induced by the 0-point energy of the transverse degree of freedom. So now we would like to combine both this effect and the rotation to explore vortex physics on this curved surface. And with this, I thank my collaborators, and especially the group of Vandelay Bagnato, with which we collaborate on this subject. And I thank you all for your attention.
Many thanks, Romain, for this very nice talk. So there are a few questions. I believe Maxime.
Yeah, hi, Romain. It's a great talk. Thanks. So I just wanted to reiterate that if Poincaré-Hopf theorem, otherwise known as a hairy ball theorem, and also in Russian literature it is called combing a hedgehog theorem, if it applies for the bubble traps, so one thing that should happen is that if you have any motion of the superfluid at all, any motion at all, you must have at least two vortices. So that would be one prediction. And the second one, and I mean, we should discuss whether it is going to be experimentally visible, that every new pair of vortices on top of the existing two, so any new pair of vortices must be compensated by a pair of stagnation points. So hyperbolic zeros in the superfluid velocity fields, and then this should be so this would be another interesting thing to observe. So I'm done with my comments.
Okay.
Yeah, I don't know if I have to maybe just Maxime. We don't have a full surface in at least in our setup, so there is hope that in the ISS they manage to do it in true microgravity environment. So what we hope to see with the motion of vortices is, let's say, can we see on Earth with this mechanism that, for example, the vortices behave, that we see that the motion is impacted by the surface curvature, for example. Okay. So it's different than what you expect from a plane.
Okay. And related to that, do you have any effects from the non-Gaussianity of the transverse state? I mean, so we, Helen and I had a paper. I mean, there's an experimental paper I mean, co-author of that covers this effect. So besides the fact that the Gaussian changes the size, transverse Gaussian changes the size, is for strong interactions you will have a modification of the Gaussian. It will become broader. I mean, do you see that?
Right now, no, but we want to probe this physics by studying the excitation spectrum, so the transverse excitations of the gas on the sphere.
Okay.
So there are a few questions in the Q&A, but I say very briefly, also connected with what Maxime said. So is there any hope to realize a torus? Because this torus, I think, is a kind of So it's another important thing of Airy-Borg theorem that you can comb. So torus, you mean it's a surface, right? I'm talking about surface.
Yes. I don't know.
Okay, I go to the Q&A. So can you please open the Q&A and maybe you read the questions?
Yes. So the first question is, thank you for the great talk. I have 3 questions. Do you see vortices in your dynamical ring? What is the upper limit on angular momentum you can impart on atoms this way? And what are the challenges in realizing the giant vortex state in your system? So the first question, do we see vortices in dynamical ring? No, because if we do a time of flight expansion, then the gas expands so fast and the density drops to very low number after time of flight, and we don't have, so it's a technical problem of signal to noise ratio. So we cannot see vortices after a time of flight expansion with this dynamical ring. From the simulation, we know that there should be still many vortices inside the system, but we cannot prove it right now. The upper limit on angular momentum, we did not try to push far in that direction. I would comment that we are still far from the equator of the bubble, so we are still quite close to the bottom, so there should be still room to increase the rotation, but I have not computed what is the limit. And what are the challenges? So to realize the giant vortex state basically would require that we lower the atom number. So for less than 1,000 atoms in our trap, we should reach the giant vortex state. And this is a challenge in terms of detection.
Okay, good. So we have a question by Wolf von Klitzen.
Hi there. Wonderful talk. Really, really nice results. I'm very impressed. I very much like the contribution from the ground state as you go to very tight confinement. One thing I really don't get is this quadrupole oscillation in the ring. So maybe you could comment upon that, because if it is a macroscopic thing, that is, if it is, not this one.
Not this one?
Yeah, this one, yes, for example, this one. So opposite ends of the ring, right? They can only communicate with each other along the ring. So, but if the ring diameter is, I'm not quite aware of what their size is, but if it is of the order of 100 micrometers, then it would take absolutely ages to get, for the information to get from one end to the other ring, right? The first excitation then is of the order of 100 seconds in time. So much, much slower than your quadrupole oscillation. Could you maybe comment upon
that? So that's a good point. So if I so first maybe the dimension here. So I don't know if, yes, I have it here. So you see our radius is something like 35 micrometer. So here the typical dimension is, as you said, 100 micrometers. And your point is that if there was a phonon traveling along the ring, it will take a very long time to carry information from one point to the other. Is that right?
So one round trip is about 20 seconds in that case.
Yes.
For the first excitation.
So so at least what I can say is that, so when we probe, so this is what we see first in the experiment. And I would say that all the atoms we impart to them So the excitation address all the atoms at the same time in the beginning. So we modify their trajectory by our excitation, and then we let the gas evolve. So so I'm not sure how the energy of the first excited state should be. So
yeah.
The other thing,
I'm not thinking so much in terms of energy, but in terms of timescales of how anything could change over this enormous distances.
Yeah, so maybe I should add that just this excited state, it has to do also with radial excitation. It's not a pure phononic excitation along the ring. So there are also the radial direction is involved,
yeah.
and this gives a much shorter time scale.
So I suggest you maybe this discussion continue. I think we also have two questions in the Q&A. So I don't think that there's enough time. Maybe you, Romain, try to address these questions separately. So you will have the questions, and then maybe you send the answer to these people separately. Okay.
Okay.
So thanks again, Romain.